Alright, so now let's see this question. So dash is an intensive property and dash is a path function. So we have intensive here and path function here. So basically intensive property the property of a system that do not depend on the quantity or amount of matter in the system. So quantity or amount of matter in the system. So a good example of this is temperature. So let's say we have a glass of water. So let's say this glass of water contain 20 liters of hot water, or let's say the temperature of the water is basically 25 degrees Celsius. So if you transport some of the water from this cup into another cup, um, let's say we pour just 5 liters of this water here into this here, the temperature is still going to remain as 25 degrees Celsius. So it does not depend on the amount of matter in the system. So however, we also have extensive properties. So basically extensive properties, they depend on the quantity of matter in the system, and a good example is mass. So let's say we have a load of 30 kg. So let's say this load is 30 kg. If you take some of this load away from this, definitely you should expect the load to become lower in weight. So probably around 20 kg, depending on the amount that you take away from the initial mass. So mass is an extensive property, not an intensive property. So you need to take note of that. So this is not an intensive property. So let's also look at volume. So let's say we have a glass volume just like we did here, and let's say the volume of water there um is 20, right? So if you pour part of this water into another glass jar, so let's say you pour 10 of volume of it. So let's say this is 10 volume of, or 10 liter rather. So let's say this is 20 liters and this is 10 liters. So definitely you expect that the volume decrease. So volume is not an intensive property. So let's look at density. So let's say we have this density of water. So this is a water of, okay, let's just say, let's use water as an example. So water has a particular density. So if you pour some amount of water here to this, the density still remains, just like viscosity. So density is an intensive property. So also internal energy of a system. So let's look at that. So let's say we have a system. So the internal energy of a system, let's say this system is composed of gas. So the internal energy is the energy contained in a system due to its microscopic components like the atoms and the molecules. So let's say you increase the number of gas molecules in this container, definitely you should expect that the internal energy should increase. So internal energy is not an intensive property but an extensive property. So we will also look at this. So entropy is entropy entropy is a state function. It depends on the change in the initial and the final state of a system. So recall that entropy of a system can be given as Q over T. So this is a change indicating initial and final value. So entropy is a state function, not a path function. So mass also is a state function, not a path function. But work is a path function. Just take note of that. Work is a path function, entropy is not. So the right answer is C, option C. Alright, so let's look at this question. So calculate the change um, in enthalpy for the reaction below, given that the bond enthalpy is at 25 or at 298 Kelvin to be this. So these are the bond enthalpy value. So for you to solve this kind of question, you need to note that. So change in enthalpy equals to bond energy or bond enthalpy, whichever one, of the reactant minus the bond enthalpy of the product will give you the change in enthalpy. So take note of the fact that it is not product minus reactant, but reactant minus product. So anytime we are dealing with bond enthalpy, not heat of formation, enthalpy of formation, no, but bond enthalpy or bond energy. So just deal with reactant minus product, not the other way around. So basically, the next thing you need to do, we've been given the equation here. So now we need to know the number of those bond there. So we have CH4 is written as this, right? So reacting with Cl and then given this, so chloromethane and then HCl. So the next thing we need to do, we need to take note of the fact that we have CH bond here. So how many CH bond can we find here? We have one, we have two, this, we have three, we have four. So these are the four CH bond. So we have four CH bond here. So we have one CL bond here. So here also we have three CH bond, right? And then one CCl bond. So for this also we have just one HCl bond, right? So let's do for the reactant first. So we have 4 in the bracket of, so the CH bond is basically positive 411, so plus the Cl bond, the chloride to chloride bond is 1 into bracket of 243. So the product aspect is 3. So we have CH bond to be 411, and then plus, let's put a bracket here. So we have a bracket here. So plus, so we have CCl bond, that's going to be 1, and then we have 3 2 7, right? So you need to take note of everything here. So what we are going to have is we're going to have, so the bond energy of the reactant is simply positive 1887. So the bond energy of the product is simply positive 1991. So the difference of the two, we have 1887 minus 1991. We therefore have negative 104 kilojoule per mole, right? So this is the answer, 104 kilojoule per mole. See this question again. So using the following bond enthalpies at 298 Kelvin, so calculate the value of the enthalpy change for NH bond. So we want to calculate the enthalpy change for a particular bond. So this is the equation, and we can also write it as NH, is 3 bond, right? 2 and then 3. So we have 2 moles of this plus 3 moles of ClCl bond. So given we have 1 mole of just N triple bond N, right? And then this, we have 6 moles of HCl bond. So this is a reactant and A is the product, right? So the bond enthalpy equals the enthalpy equals the bond energy of reactant minus bond energy of product. We're given the enthalpy of the reaction. So the enthalpy of the reaction is negative 464 kilojoule per mole, right? So equals to, so let's look at this. We are told to calculate the enthalpy change for NH bond. So we don't know this yet. but we have it to be how many NH bond do we have here? We have 1, 2, and 3. So everything is going to be 6. Like let's keep it simple. 2, 3, NH bond, right? So everything is basically 6 NH bond. So plus, so we have this to be 3 into bracket Cl bond, and that's 2, 4, 3. So this is the reactant, right? So let's see the products. So the N bond, so the triple bond, the nitride bond, right? So we have it to be 942 plus 6 of this HCl bond. So we have it to be 431. So everything here becomes so when you evaluate everything, we have it to be 6 NH bond to give positive 2, 3, 3, 4 bond. So basically we have that NH bond gives us positive 389 kilojoule per mole. So this is option D. Alright, so let's look at this question. So calculate the heat of formation of methane given its heat of combustion. So let's write the equation for the combustion of methane. So when the methane is combusted, so we have it to be CH4 gas reacting with oxygen gas to give CO2 gas and plus H2O, which is liquid. So we need to confirm that the reaction is balanced. So for the reaction to be balanced, oxygen is 2 here and oxygen here is 3. So if you put 2 here, this gives oxygen over 4, and let's put 2 here. So the equation is balanced already. So now the O heat of formation of, so calculate the heat of formation of methane. So the heat of combustion of methane A is negative 891 kilojoule per mole, right? So given that the heat of formation of CO2, so CO2 to be negative 394 kilojoule per mole, and water to be negative 286 kilojoule per mole, right? So we're told to calculate the heat of formation of methane. It's unknown. So we have no value for the heat of formation of oxygen because it's not a compound. It's just so it's not a compound rather. So this is not a compound. So unlike the heat of the bond energy calculation, where we had to use reactant minus product, for this case we are using heat of combustion equals to change in enthalpy of the product minus change in enthalpy of the reactant, right? So this gives us, so these are the products, these are the reactants, and we therefore have that negative 891 equals to, so we need to see the products. We have minus 394, and this we will always have to take note of the coefficient of the reactant of product. So we have it to be plus 2 in the bracket 286 kilojoule per mole, right? So this is the product minus, so the reactant is X, because we do not know the value of the heat of formation of methane yet. So for us to now finalize this, we have our X to be to be so we have it to be equals to negative 394. So this becomes, we have minus 572, and this, so this comes here and this comes in, so we have X equals to positive 891. So everything here becomes negative 75 kilojoule per mole. So this is option A, right? Alright, so looking at this question, the gas is confined to a cylinder under constant atmospheric pressure. So the atmospheric pressure is constant. So it's the same thing as P external to be constant, right? So when the gas undergoes a particular chemical reaction, so it releases this amount of heat to the surrounding. So Q equals to negative 85 kilojoule because it's losing into the surrounding, and it does the work of 36 kilojoule on the surrounding. So this is also negative. So this work is done. This heat is released to the surrounding, and this work is done on the surrounding. So we need to calculate the change in internal energy of the system. So change in E equals to Q plus W. So therefore we have that negative 85 plus negative 36. So we have this to be um, negative 121 kilojoule, right? So looking at this, calculate the change in internal energy of the system for a process in which the system absorbs so Q equals to positive 140 joules because the system absorbs this amount of heat from the surrounding and does this amount of work on the surrounding. So that's 85 joule, right? So we have change in E to be equal to Q plus W. We therefore have that this is 140 minus 85. So this gives us 55 joules. Alright, so looking at this question, hydrogen peroxide is decomposed to water according to the equation here. So the heat that accompanying the reaction is negative 196 kilojoule. So we are told to calculate the change in enthalpy value when 5 gram of hydrogen peroxide decomposed. So basically we have that we are dealing with hydrogen peroxide in this question. So we have 2 moles of hydrogen peroxide under its decomposition gave negative 196 kilojoule of heat. So let's find the molar mass here. We have 2 to be 2 times 1 plus 16 times 2, right? So this gives us 2 plus 32, right? So this is 2 into bracket 34, and this gives us 68 gram per mole, right? So this gives negative 196 kilojoule. So how much heat will be generated when we are dealing with just 5 gram of this of 5 grams? So it's going to be x here. So let's cross multiply, and we have x to be 5 times negative 196 over 68. It to be negative 14.41 kilojoule. So this is the answer, option D. So let's look at this question. Calculate the change in internal energy of a system. So looking at this question, change in E of a system for a process in which the system absorbs. So if the system absorbs 140 heat, 140 amount, 140 energy, that will be positive, right? So and thus this work done on the surrounding will be negative. That's 85 joule, right? So we need to calculate the change in internal energy, which is Q plus W, and that will give us positive 140 minus 85. So this will give us 55 joule. So we have this to be this. So let's see this question. Water has a specific heat capacity of this. So 100 100 kilogram of it. So the temperature of 100 kilogram of water was raised by this amount. So we need to calculate the amount of heat absorbed by water. So basically the heat absorbed is the same thing as MC change in theta, where M is the mass of the substance and C is the specific heat capacity, right? So this is a change in energy, a change in temperature. So we have that what this, so calculating the amount of heat, so we have it to be m equals to, so 100 gram times the specific heat capacity will be 4.18 joules per kilogram, um joules per Kelvin per kilogram, per gram rather. So and then we have a change in temperature to be 2 Kelvin. So we have that Kelvin cancel Kelvin, gram cancels gram, and therefore we have that it's equals to 836 joule, right? So the answer is option B. This question also, how much heat is needed to warm mass? This is the mass, 300 gram of water from, so let's see the change in theta to be 95 degrees Celsius minus 20 degrees Celsius, and that should give us 75 degrees Celsius. So the specific heat capacity of water is 4.18 joule gram per mole kilogram Kelvin per mole rather. So how much heat is needed? So heat equals to mc change in theta. So therefore I have that 300 gram times 4.18 joule per gram per Kelvin, right, times change in theta, which is 75 degree Celsius. So we are working with Kelvin here because the specific heat capacity here is specifying the temperature to be in Kelvin. So this cannot work together. We need to convert this to Kelvin also. So that will be plus 273, and therefore we have it to be, so we have it to be 348 Kelvin. So the next thing we need to do is to cancel this cancels out. So this becomes 348 Kelvin, and this cancels out as well. So we have this, we are left with 300 times 4.18 times 348 joules, right? So we have the answer to be 436.4 kilojoule. So we need to take note, looking at the answer here, none of the options matches with the answer. So definitely we have to look at this, like most likely this is wrong. Probably if this was degree Celsius, maybe we would not have converted this to this Kelvin, and we wouldn't have used this. So we need to figure out, that is a question problem, not our own problem. So but if this was degree Celsius, we don't have to convert this to degree Celsius anymore. We just have to like do this straight away, and then we should get one of the answers here. Alright, so let's look at this question. Calculate the standard enthalpy change when ethanol is combusted. So using the bond energies value, these are the bond energy values that were given. So we're told to calculate the standard enthalpy change. So the standard enthalpy change is equals to the bond energy of the reactant. Always take note of the fact that it's reactant minus product when it's bond energy. So we have this to be product. So therefore we have the combustion equation is let's put it this way, C2H5OH plus 0 oxygen gas to give CO2 plus H2O. So we need to balance the equation. So we have two atoms of carbon A and one A. So let's make it two while adding two moles here. So carbon is balanced. So let's look at hydrogen. We have 5 plus 1, 6. So we have just 2 here. So let's add 3 here. we make it 6, right? So is the oxygen balance. We have 1, we have 2 here, that's 3. So here we have 4 and 3, that is 7. So we have 1 here, 1 minus 7, that's 6. So we have 3 here, everything is balanced, right? So now, so let's look at the bonds that are formed, that are in the reactant and the product. So we have hydrogen, hydrogen, hydrogen for this carbon and this one to form the ethanol. So hydroxide here plus 3 moles of oxygen gas. So it's given 2 moles of COO and 3 moles of hydrogen gas, right? Hydrogen water molecule rather. So therefore we have that we have how many CH bond here? So we have 1, 2, 3, 4, 5. So we have 5 CH bond plus we have CC bond. We have 1 CC bond. So we have CO bond. So we have 1 CO bond, and we also have OH bond, which is 1. So plus OH bond. So we also need to add this 3 O bond. So this gives us the reactants. So let's find the value. So we have 5 in the bracket of, so the CH bond is 410, right? Plus the CC bond is 347, plus the CO bond is 336, and the OH bond is 465, plus the OO bond, which is 496. So everything here becomes 4686, right? So now looking at the product, we have that the product is 2 of we have again 2 of C double bond O bond. So like we have 2 of C double bond O bond, 2 of it here inside, and then we have the outside 2 here, which is the number of moles. So plus 3. So we have OH bond twice, that will be 2 OH bond, right? So this should give us that's 2 times 2 times 805. So we have it to be CO bond. So C double bond O. So that's 805. So plus, so we have 3 times 2 times 465, right? So everything here should give us 6010. So when you subtract this and this, you have 4686 minus 6010. So this should give us negative 1324 kilojoule. So the right answer is option A. So what is the work done by a system if this amount of heat is supplied? So this is the system. We have the system here. So 460 joules of heat is being supplied. So Q equals to positive, right? Positive 460. So causing an increase in internal energy. So changing E equals to 200. So what is the work done by a system? The work done by a system is different from the work done on the system. So we have change in E equals to Q system plus work done on the system. So we have that this to be 200, and this Q is positive here, right? So that's plus 460 plus work done on the system. Take note of this. this is work done on the system, not work done by the system. So work done by the system is negative, work done on the system is positive. So we have work done on the system is here we have it to be 200 minus 460, right? So we have this to be negative 260 joules, right? So now to now get the work done by the system to the surrounding, that is basically the negative of this. So that gives us work done on the surrounding, that's um positive 260 joules. So calculate the internal energy for the combustion of 1 mole of liquid benzene when the reaction is run in power bomb at 298 Kelvin. So the enthalpy of the reaction at this temperature is this. So benzene is C6H 6, right? So liquid benzene, so it's being combusted. So we have it to be CO2 plus H2O, right? So the next thing is to like look at the six. We have six carbon here. So let's put six carbon here also. So the next thing is that the carbon is balanced, is the hydrogen balance. We have six hydrogen here. If we have three hydrogen here, will it make it balanced? So this hydrogen is balanced here and also here. So now let's look at oxygen. We have two atoms of oxygen here. So here we have 12 and then 3, that's 15. So let's simply add um 7.5 here, or you can multiply through to have a whole number, not a fraction. So we have 7.5 here. So the next thing we need to do is to find the already given the enthalpy. So the enthalpy H is the same thing as enthalpy of the product minus that of the reactant, right? So we have this to be the products and these are the products. So also these are the reactant. So we are going to calculate the internal energy for the combustion. So basically we're not given the heat of formation. So we really cannot use the formula because we're not given the heat of combustion, the heat of formation of the product and the reactant. So what we need to do is changing heat is the same thing as changing E internal energy plus P changing V, right? So note that this is the same thing as nRT, that is changing nRT, that is P changing V equals to changing nRT. So note that only changes in moles of gaseous reactants are considered. So therefore we have that change in E, the internal energy, equals to um, change in H minus P change in V. So therefore we have that change in H to be this, right? We have it to be minus 3264.64 kilojoule minus. So we have this to be, so for us to get the number we have change in n. So recall that this change in n only works for gaseous reactants here or gaseous products. So let's look at the balance equation here. So this is gas, so this is also a gas, and this is a liquid, right? So change in n will be 6 minus 7.5. So we have it to be 1.5, right? So therefore we have a P change in V equals to 1.5 times 8.314, which is this, times the temperature, which is 298 Kelvin. So 298. So everything here becomes so we have it to be 3716.358. So let's put it in kilojoule also. So this becomes 3.7 kilojoule. So everything here becomes negative 32609 kilojoule. So which can approximate to negative, let's put negative there, 3261 kilojoule. So we have it to be option B. So looking at this question, hydrogen peroxide can decompose to water and oxygen by the reaction. So hydrogen peroxide can decompose to water and oxygen. So we need to take note of the fact that this is two. Like what we have here is simply 2 moles of hydrogen peroxide. Please take note of that. So it gives 2 moles of water molecule and 1 mole of oxygen. So calculate the change in Q when the hydrogen peroxide is 5 gram. So all we need to do is this. We have 2H2O2. The enthalpy of formation is the enthalpy of the reaction here is negative 196 kilojoule, right? So and this is the same thing as we have this one to be 2 plus 32, and this is 16 times 2, so this is negative 196 kilojoule. So this becomes 34, and that gives us 68 gram per mole, and this gives us negative 196 kilojoule. So 5 gram there will give us this, and we don't know the value of its energy. So let's cross multiply. We have x to be 5 times negative 196 over 68. So we have this to give so negative 14.41 kilojoule. So we have this to be the answer. So all of the following thermodynamic properties are intensive except this prayer. Take note. Alright, so this reaction says we should calculate the enthalpy of for the reaction using the thermodynamic equation. So we needed to calculate, it's more or less like calculating the enthalpy of formation of C2H2, right? So we needed to calculate the enthalpy of formation of this. We already know the enthalpy of formation of this. We know the enthalpy of formation of this. So let's use this equation. So we have that the enthalpy of formation of this enthalpy of this reaction basically uh, equals to change in enthalpy of the product, not reactant. We only use reactant first in case of bond energy. So minus enthalpy of the reactant. So basically we have this to be negative 25988 kilojoule per mole equals to, so this we have it to be 4 CO2 plus 2 H2O, so everything minus 2 C2H5. So we don't deal with this because it's a it's not a compound. So looking at this, we already have the heat of formation of carbon dioxide here, so we have it to be used here. So also the heat of formation of H2 is here, right? So we have it here. So what we need to do is input the values. We have 259.8 equals to 4, and so CO equals to this, we have it to be negative 393.5 plus 2, so H2O is negative 285.8, right, minus 2, so we have this to be C2 C2H2, sorry, not 5, C2H2. So we need to get that C2H2. So our answer is equals to uh, negative 226.6 kilojoule. So we have it to be this. So this question says calculate the mass of ethane which must be burned to produce this amount of heat using the reaction. So given the reaction A, so we have that 2 moles of ethane produced negative 3120 kilojoule of heat. So this is the same thing as 2. We have C2H6, which is 2 into bracket 12 times 2 plus 6, and that's 2 into bracket 24 plus 6, and that's 2 times 30, which gives 60 gram per mole, right? So we have 60 gram per mole to be given to produce this amount of heat. So how much gram will produce 100 kilojoule? So let's put this as x. So cross multiply. We have 60 times 100. So it's negative over negative 3120. So this cancels out. This cancels out. So therefore we have that x equals to 1.923 gram. So simply put this option B. Which of the following thermodynamic functions is not a state function? So eat and work. So eat and work are not state functions. So this. So given the bond energies of the following molecules, so calculate the enthalpy of the reaction. So all we need to do is this. So changing it equals to bond energy of reactant minus bond energy of product, right? So therefore we have that so we have this is a reaction. So the reactant, let's write it out. We have it to be hydrogen gas. So we have 2 moles of it plus 2 moles of chlorine gas, and the product which is hydrogen chloride. So we have 4 moles of this. So therefore we have this to be 2, and this bond is 436 plus 2. So this is 243, right? Everything minus 4. So we have HCl to be 431. So we have it to be 872 plus 486 minus 1724. So everything equals to negative 366 kilojoule. So we have it to be D. Alright, so the question says calculate the change in internal energy. So internal energy is or this for the reaction of the formation of 1 mole of ammonia from the reaction below. So basically we have that change in enthalpy is the same thing as change in internal energy plus P change in B, right? So the enthalpy was given to be negative 92.72 kilojoule. So we have that the um so we are told to calculate this. This is unknown. So this is the same thing as n change in nRT, right? So we need to calculate the change in n, and this only deal with the gaseous reactant and product. So we have 3 moles. So this is n of products minus n of reactants, right? So we have it to be 3 2 rather 2 minus, so the reactant is just 3 and 1, so that's 3 plus 1, and that gives us 2 minus 4, which is minus 2, right? So therefore we have that this becomes negative 2 times our R is 8.314 times the temperature of 25 degrees Celsius is the same thing as 25 plus 273 give 298 Kelvin. So this is 298. So everything here will be used in the equation. So we have that change in internal energy equals to change in H minus uh, change in nRT. So we have it to be negative 92.72 minus 4.96 kilojoule. So because this is kilojoule already, so take note of that. So this was also placed in kilojoule. So we have negative 92.72 plus 4.96, and this gives us negative 87.76 kilojoule. So option D. Alright, so in this question, for which of the following reaction is changing H same as the internal energy? So recall that we said changing H is the same thing as changing E plus P changing V. Recall also that internal energy can be written as E or U, right? So we have this. So also recall that P changing V is the same thing as changing nRT, right? So we can simply say that changing H equals to changing U plus changing nRT. So we can only have changing H to be equals to this if this is 0, and because R are constant, T are constant, so they cannot be the variable. So this is the only variable changing n, and so changing n is change in the number of moles of the gaseous products minus the number of moles of the gaseous reactant. Take note that we're only dealing with gaseous ones. So looking at this, the change in n is we have 1 here, and this 0, this is 0. So 1 minus 0, so this is 1. So for this, we have change in n to be this, so 3, and this 4 minus 1. So 4 minus 1 equals to 3. So this also, everything is solid, so change in n equals to 0. And this, we have it to be 1, because this is liquid here, except if it's gas. This is liquid, and this is gaseous, right? So we have this to be 2 plus 1. So this is 3. So therefore we have it to be changing n equals to 1 minus 3 equals to minus 2. So this is the only case we have n equals to 0. So therefore option C is the answer. Alright, so calculate the standard enthalpy of formation of styrene if its heat of combustion is this. So basically styrene is C8H8, and its combustion with oxygen should give CO2 plus H2O. So now let's balance this. So we have 8 atom of carbon. So let's put 8 here. So carbon is balanced. So hydrogen we have 8 here. So let's put 4 here. Hydrogen is balanced. Now oxygen we have 16 oxygen here and 4. That's 20, right? So let's put 10 oxygen right here to balance the equation. So now we're told that if its heat of combustion is this, so the heat of combustion of styrene is negative 4395.2 kilojoule per mole, right? So now we're given this, so we're told to calculate the standard enthalpy of formation of styrene. So what we need to do is change in enthalpy of the combustion of styrene equals to change in enthalpy of the product, yeah, minus change in enthalpy of the reactant. So the heat is negative 4395.2 equals to, so the product we have it to be 8, so the CO2 is negative 393.5 plus, so we have oxygen and water molecule, so we have it to be negative 285.8. so everything minus, so the reactant, so the reactant here is unknown, styrene. So but this is not a compound, so we have it to be plus 0, right? So what we need to do next is to evaluate this to get so we have negative 4395.2 equals to so all of this is, so we have negative 4291.2 minus x. So the next step we need to do is that we have x equals to negative 4291.2 plus 4395.2. So we therefore have our x to be 104 kilojoule per mole. So the answer is D. So this question we have n equals to 1. One of the mole of an ideal gas at the temperature is 25 degrees Celsius, which is the same thing as 298 Kelvin. You know, when we add 2 plus 273, give this. So the gas expand reversibly, right? So since the gas is expand reversibly, we have work to be negative 2.303 nRT log. So now the volume, okay, we are having volume here, and that will be V2 over V1. So the next thing becomes calculate the work done by the gas. So this formula gives us work of a system, right? So for us to get the work done by the gas, the whole equation must be negated. So we are going to have work by gas equals to positive, or simply put it this way, negative of negative 2.303 nRT log V2 over V1, which gives us positive 2.303 nRT log V2 over V1. So therefore we have that we have it to be 2.303. So the number of moles is 1 times 8.314, which is gas constant, times 298, which is the temperature, and then we have log of V2 is 20 over 10. So we have it to be um 1717 point 6 joules, right? So now for us to convert this to calorie, we have that um 1 calorie equals to 4.184 joules, right? So having 1717.6 joules, let's call this x. So therefore we have that our x equals to 1717.6 over 4.184, which gives 410.5. So the answer is this. Remember that this is positive. Everything we got here is positive. So it's positive. They asked for the work done by the gas, not the work done on the system.